Hey there, and welcome back to 4.4. We're going to look at the second half of this section today on graphing polynomial functions. So yesterday we talked about evaluating polynomial functions. Today we're going to look at the second objective, which is to be able to identify general shapes of graphs of polynomials. Again, still leading to this standard on graphing polynomials. And so looking at where we left off yesterday, we're going to look at a couple of graphs here. And you'll see there are a couple links in your notes, and you can open those links and see the functions that are graphed here. But just briefly, I'll talk about what graphs these are. This is x squared, and then we come to x to the fourth, and the green one here is x to the sixth, and the purple is x to the eighth. Okay, and so the question is, what do you notice about the end behavior of these graphs? Well, as x goes to positive infinity, where's the y going? Well, as x goes to positive infinity, where's y going? Y is going to positive infinity. And as x is going to negative infinity, where's the y going? Well, the y is going to positive infinity, right? Because it's going upward. Now, what do you notice about these functions that we had here? X squared, x to the fourth, x to the sixth, x to the eighth. Well, look at the powers. They're all what? They're all even. And so if we have an even powered function, the end behaviors will go in the same direction. Positive to the right, positive to the left. In the second graph, we see we've got 5 lines drawn on here. And this one is x, and then x cubed. The blue is x to the fifth. The green is x to the seventh, and the purple is x to the ninth. So let's first talk about the end behaviors. What do you notice about the end behaviors here? Well, as x goes to positive infinity, where's the y going? Well, they're all going up. Now, the rates at which they go up are different, but they'll all, as we continue going on and on forever, they're all going to eventually lead out to positive infinity. And as x goes to the left, going towards negative infinity, where's the y's going? Again, they're all going in a downward direction, which means they're all leading towards negative infinity. And what do you notice about these functions? Well, remember, x can be rewritten as x to the first, x to the third, x to the fifth, x to the seventh, x to the ninth. All of these are odd degreed functions. And so odd degree functions will have this end behavior. Now we're going to talk about some transformations and things as we go through this section that we've talked about back in chapter 2, bringing those back up today. So let's talk about the next question here. What happens when the leading coefficient is negative? So all these right now are just x to the first, x to the third, x to the fifth, x to the seventh, x to the ninth. And if you want to go back and look at Desmos and see what happens by plugging in the negative to this or plugging in the negative to this on the different functions, what happens to those graphs? Well, remember that the negative out front, and this is talking about going back to chapter 2, is a reflection where? A reflection across the x-axis. Because remember, it's going to affect the y value. So it's going to take this orange line and change it so that now it's going to go down this way, and this piece would go up this way. Or if I'm looking at one of my higher powered functions, it would take this red and put it down here. And it would take this red and put it up here. Because remember, we're reflecting across the x-axis, not the y-axis here. The result would be the same for this individual function, but for any translated function, it would make a difference. Okay? So let's talk about the zeros of odd and even powered functions, or even degreed functions. Odd degree functions will always have an odd number of real zeros. So for example, if I have a fifth degree function, then the number of zeros it can have is either 5 real zeros, 3 real zeros, or 1 real zero. And the same holds true for even degree functions. So let's say I have an 8th degree function, right? Well, how many zeros could it have? It's an even number of zeros or no zeros at all. You know, we're talking about real zeros here, not imaginary roots or complex roots. So an 8th degree function could have 8 real zeros, or it could have 6, or 4, or 2, or it could have no real zeros. And again, we're going to look at the graphs here in a minute to see why this is. So let's look at example 4 here. For the graph, determine the following items. The end behavior, if it's an odd or even degreed function, determine the signs of the leading coefficient, and state the number of real zeros. Okay, so let's start with the first piece. What is the end behavior? As x goes to positive infinity, f of x is going where? Well, in this case, as x goes to positive infinity, y is going to negative infinity. And as x goes to negative infinity, f of x goes where? Well, as x goes to negative infinity, the y is going to negative infinity as well. Okay, so we have our behaviors. Is it an odd degree or even degree function? Well, that's related to the fourth bullet point, right? Stating the number of real zeros. Well, how many real zeros does this have? It never touches the x-axis, so it has no real zeros. Well, if it has no real zeros, and the end behaviors are going in the same direction, that means that this must be an even degreed function. Okay? And lastly, determine the sign of the leading coefficient, because we've already done bullet point 4. So again, this was bullet point 1, this is bullet point 2, this is bullet point 4, or this is 4 and this is 2. So the last bullet point here, determine the sign of the leading coefficient. Well, normally an even degree function, remember, look at our graphs that were above, right? Normally an even degree function looks something like this. But this one's opening down and down. So something changed that, which means that my leading coefficient has what sign? My leading coefficient is negative. And so again, just by looking at the graph, we can start to see pieces of this coming together. Okay? So let's look at this graph. Again, we're going to do the same 4 pieces. Describe the end behavior, determine whether it's an odd or an even degreed function, determine the sign of the leading coefficient, and state the number of real zeros. So as x goes to positive infinity, where is the y going? Where is f of x going? So as x goes to positive infinity, the y is going where? To positive infinity. And as x goes to negative infinity, where is f of x going? Well, we look at it as x goes to negative infinity, y is going where? To negative infinity. So that gives us our first piece. Remember, these two are linked together. So how many real zeros does it have? Well, how many times does it cross the x-axis? This has 1 real zero. Well, it's an odd number of real zeros, which means this is an odd degree function. And finally, determine the sign of the leading coefficient. And so looking at our end behaviors, the right side's going up, the left side's going down. This is the normal behavior of an odd degree function. So the leading coefficient is positive. Now, I'll give you a little trick to knowing the leading coefficient very quickly. The right end behavior will always lead to your sign. The right end behavior here is positive, so my leading coefficient is positive. In the previous problem, our leading coefficient was negative, and look where our right end behavior goes. It goes to negative infinity. And so as long as we're going to one of the infinities, that end behavior will hold true for most parent functions. Again, as we get to like trig and precalculus, we'll deal with some things there because they don't go to infinities every time. But for most things, it will follow that pattern. And so example 5, graphing the polynomial using a table of values. We've got f of x equal to negative x cubed minus 4x squared plus 5 by a table of values. And you'll see I've got a graph down here at the bottom for us to look at. So let's set up a table. And I'm going to start at 0 because that's the easiest thing to deal with. And then we'll go towards the positives, and then we'll come back to the negatives in a minute. And so there's my y, and of course this will become the order pairs that we're going to plot on the graph. And so plugging in 0, of course I'm going to get the opposite of 0 cubed minus 4 times 0 squared plus the 5. And of course that becomes 0 and that becomes 0, so this is just 5. So I get the order pair 0, 5. When we plug in 1, we're going to get the opposite of 1 cubed minus 4 times 1 squared plus the 5. Remember your order of operations here. So you're going to get 1 squared is 1. This is 1 cubed is 1. So you're going to get negative 1 minus 4 plus 5. Well, negative 1 and negative 4 is negative 5, and plus 5 would give us 0. And so we end up with 1, 0. For 2, we're going to get the opposite of 2 cubed minus 4 times 2 squared plus the 5. And so we're going to get negative 8. This will give us another negative 8, so that's negative 16. And plus the 5 would take us back to negative 11. And so I'm at 2, negative 11. Let's go to 3 and see what happens. The opposite of 3 cubed minus 4 times the 3 squared plus the 5. And so I end up with negative 27. This is negative 9, and times of 4 is negative 36. So negative 27 and negative 36, that is a negative 63. Plus 5 will give me a negative 58. And so I'm at 3 and negative 58. Do we think that this is going to return back? If I keep plugging in 4, 5, 6, do we think this is going to work our way back towards the x-axis? In this case, no. Okay, so I have those points. So I'm going to plot 0, 5. It was 1, 0. And then my next point was 2, negative 11, so I'd just be off the graph here. So again, I've got this piece at this moment. The question becomes what's happening to the left. And so let's do negative 1. So we get the opposite of negative 1 cubed minus 4 times negative 1 squared plus the 5. And so that's going to give me negative 1 cubed is still negative 1, so that's a positive 1. Negative 1 squared is positive 1 times negative 4 gives us a negative 4. And so positive 1 minus 4 plus 5. And so positive 1 and 5 is 6, minus 4 gives us 2. And so I'm going to be at negative 1, 2. And we go to 2. So the opposite of negative 2 cubed minus 4 times negative 2 squared plus the 5. And so this is going to give us a negative 8, which makes it positive 8. This is going to give us a positive 8 times a negative 4 is negative 16. So I've got positive 8 and negative 16. That is negative 8. And negative 8 plus 5 is negative 3. So I end up between negative 1 and negative 2. I'm crossing the x-axis somewhere in there. Let's go to negative 3 and see what happens. So the opposite of negative 3 cubed minus 4 times the negative 3 squared plus the 5. So this is going to be a negative 27, goes positive. This is a positive 9 times the negative 4. So this is a positive 27 minus 36. That is negative 9. And negative 9 plus 5 is negative 4. And so we see there's some slowing here, right? So let's go to negative 4 and see what happens. So we're going to get the opposite of negative 4 cubed minus 4 times negative 4 squared plus the 5. And so this is negative 64 with the negative out front will make it positive. This is a positive 64 with the negative 4 will make it negative. So 64 minus 64 is 0. So we're just left with the 5 again. And so as we see, between negative 3 and negative 4, we're crossing the x-axis. And so let's go one more number. Let's go to negative 5 and see what happens. So negative 5 cubed minus 4 times the negative 5 squared plus the 5. So this is going to give us a positive 125 when it's all said and done. This is 25 times negative 4 is 100. And so we're going to get 125 minus 100 is 25 plus 5 gives us 30. Do we think this is coming back from this direction at this point? The answer is no. And so we're going to plot the points that we have found at this point. So we've got negative 1, 2. We've got negative 2, negative 3. Negative 3, negative 4. Negative 4, positive 5. And then negative 5 is positive 30 way up there. And so as we look at this function, we start to see what it's going to look like. And again, doesn't necessarily mean that it's turning at that dot there. It could be going like this and then back like this. But we see that the end behaviors are consistent with the degree and leading coefficient. Our leading coefficient was negative, which is going to flip our end behaviors. And the odd means that our ends are going to go in opposite directions. So our end behavior here, as we look at our sign, our leading coefficient, as x goes to positive infinity, the f of x is going to negative infinity. And as x goes to negative infinity, the f of x is going to go to positive infinity because we're going up in this direction. And that's the basic premise of this. That's all I have for us today. Use the table, plug in the values to get your order pairs to plot them on the coordinate plane. And again, think about your end behaviors with your leading coefficient and the power of your function. So is it an even degreed function or is it an odd degreed function? And think about those end behaviors. So if you got questions, you know what we got to do. We're going to look at the assignment tomorrow in class, but make sure you write down those questions that you do have, and I hope y'all have a great night. Bye. But not really, because I forgot the word of the day. And so the word of the day is end behavior. Again, the word of the day is end behavior. And now I'll see y'all tomorrow.